For years, the industry consensus held that AI required separate systems, one neural network module to perceive the world and another to generate an action. Now, we are seeing those discrete parts seamlessly integrating. Historically, developers forced these disparate systems to communicate by building a latent space bridge. This translated the understanding from a perception module into the commands required for an action module. A dense cluster of releases from week 48 indicates that this structural fragmentation is actively being engineered out of frontier models. This diagram shows standard clip and diffusion nodes connected by traditional pipelines, which then collapse into a single unified mixture of experts node. A mixture of experts, or MOE, is a neural network architecture where parts specialize in processing specific data types, activating only when needed. By unifying the architecture, this physical collapse eliminates the data bottlenecks inherent to legacy vision language models. A vision language model, or VLM, is an AI designed to process text and images simultaneously. Eliminating these bottlenecks produces two specific operational outcomes. It collapses video generation inference times, and it makes localized edge robotics mathematically viable. Multimodal systems are no longer stitched pipelines. They are natively interleaved engines built for simultaneous perception and action. The benchmark for this unified training approach is the Transfusion paper, released jointly by Meta and NYU, which details training a single model from scratch. This schematic illustrates a neural network architecture processing two distinct streams concurrently. Next token language loss applies to text, and diffusion loss to images, simultaneously through the same transformer blocks. As data increases, the mixture of experts dynamically scales, resulting in genuine world modeling behavior. In the open source community, the Neo-Unify model serves as a corroborating data point for this methodology. Neo-Unify specifically bypasses the traditional bridge entirely, choosing to natively interleave understanding tokens and generation tokens right at the base layer. These releases validate a structural hypothesis. Traditional discrete encoders are not load-bearing pillars of AI architecture. They are legacy processing bottlenecks. Bypassing the traditional encoder removes inherent latency and data degradation, altering how base models parse complex realities. These foundational optimizations also apply to video inference, enabling fluid, high-fidelity temporal generation natively on local machines. The Spectrum project recently achieved a massive jump in processing speed, yielding a 3 to 5 times speedup. This chart tracks a diffusion denoising path, using a secondary arc to show Chebyshev polynomial step prediction. By accurately predicting steps ahead, it skips redundant evaluations. Critically, this logic applies across image and video pipelines without retraining the base model. Moving from mathematical theory to community deployment, the LTX 2.3 model has become the primary case study for fast local inference. Within days of release, the community built rapid local workflows heavily compressed into 12 GB GGUF formats. GGUF is a highly compressed file format that allows massive AI models to run efficiently on standard consumer hardware. This allows native text-to-video and video-to-video pipelines to execute entirely on consumer-grade GPUs. The community immediately integrated ConfigUI nodes to handle physics-based post-processing on these generations. Applying depth-aware bokeh and halation mathematically reduces the synthetic artifacts typical of AI-generated video. Raw algorithmic efficiency, combined with aggressive GGUF standardization, has successfully decentralized frontier video synthesis away from massive cloud compute clusters. This push for efficiency extends to embodied AI. Current robotics research is now strictly focused on deployable, low-latency physical engineering. The Utonia architecture solves the persistent issue of negative transfer between differing spatial sensors. Negative transfer occurs when an AI's training on one specific task degrades its ability to perform a separate, related task. This maps a Utonia pipeline handling noisy 3D point clouds from LiDAR and RGBD sensors. LiDAR measures distance with lasers, while RGBD captures color and depth. A single universal encoder standardizes this perception, regardless of scale or viewpoint. This newly standardized perception data solves a major bottleneck for the light VLA edge architecture, which is built for embedded hardware constraints. Running these vision language action pipelines locally requires post-training quantization. Quantization is a compression technique that reduces precision, drastically cutting a model's memory requirements. By shrinking the memory footprint, quantization mathematically ensures the model fits directly onto constrained edge computing devices. To control these edge devices, developers use techniques like multimodal behavior tree generation as the software layer. Behavior trees are mathematical execution frameworks that break complex commands down into a sequence of simple modular tasks. Small local VLMs are generating reliable robotic task plans as these compact behavior trees, instead of relying on heavy cloud inference to decide their next physical move. As a final safeguard, the CRAP plus audio-visual LLM architecture targets negative transfer to ensure multitask reliability across these local agents. Cloud-dependent robotic brains are an evolutionary dead end. The industry standard is localized, quantized inference processing, standardized multimodal inputs directly on the edge. We are seeing three distinct engineering vectors converge: unified base architectures, mathematically accelerated video inference, and quantized edge robotics. These foundational breakthroughs are mapping directly to frontier outputs, like the 14 billion parameter Helios model executing text, image, and video generation in real time. Simultaneously, edge perception breakthroughs tie directly into systems like OmniExtreme, pushing the boundaries of dynamic physical movement and stability benchmarks in humanoid control. The immediate future of this convergence is clear. OpenAI's framing of GPT 5.4 is explicitly designed around combining computer use and vision natively. Vision and action are no longer separate, siloed modules passing degraded data. They are converging into singular, continuous loops of physical and digital intelligence.